Hello there, and welcome back to this sleepy corner of the universe. I'm glad you're here. Tonight, we're going to drift towards something so distant, so powerful, and so strange that it almost feels like a myth. An invisible heart of gravity, sitting more than 10 billion light years away, quietly reshaping everything around it. Astronomers gave it a calm, almost bureaucratic name, TON 618, just a catalogue entry at first, a tiny radio source on a list. But behind that simple label lies one of the largest black holes we've ever found, a gravitational giant weighing tens of billions of suns, an object so bright it can outshine entire galaxies. Yet, at its core, it is pure darkness, a place where light itself has no way out, and where our best equations quietly fall apart. As you settle in, let your body grow still. Feel your shoulders soften. Let the day slide off you, like dust drifting out of a beam of light. Tonight, you don't have to solve anything, fix anything, or remember anything. You're just here to listen. Imagine the universe not as a cold emptiness, but as a vast ocean of time with waves made of light. Every star, every galaxy, every collision sends ripples across that ocean. Some of those ripples have been traveling since long before Earth existed, quietly crossing the dark for billions of years. Some of them come from TON 618. When that light first left its home, the universe was young and restless. Galaxies were still forming. Space was thicker with gas, brighter with radiation, louder with creation. And in the middle of one of those newborn galaxies, TON 618 was already feeding, swallowing gas, releasing light, carving its own bright scar into the early cosmos. We can't see the black hole itself. No one can. But we can see the light from everything falling toward it. We can see the glow of its swirling disk of plasma. We can measure its echo in radio waves and X-rays and feel its mass through the way it bends space. Tonight, we'll follow those echoes. We'll stand, in imagination, at the edge of its event horizon, the boundary where light loses its freedom. We'll listen to the faint signals that left it more than 10 billion years ago. We'll watch galaxies form, black holes merge, and the universe slowly learn how to organize itself. And somewhere, as we drift through these distant scales of time and space, the rhythm of the cosmos might begin to match the rhythm of your breathing, in and out, galaxies forming and fading, thoughts arriving and dissolving. You don't need to hold on to any of it. Just let the story wash over you, like starlight crossing the dark. When you're ready, we'll begin. Chapter 1. A name in a catalogue, a monster in the dark. If you were an astronomer in the mid-20th century, you might have first met TON 618 inches, the most understated way possible, as a line of text, not a dramatic photograph, not a glowing picture in a headline, just an entry in a radio survey made at an observatory in Mexico, a compact, bright radio source, noted almost in passing. At the time, no one knew exactly what these sources were. They appeared in places where no familiar star or galaxy could be seen. Through early telescopes, they looked almost like stars, tiny and point-like, and so they were given a name that reflected that confusion. Quasi-stellar radio sources, quasars. TON 618 was one of many. For years, it sat quietly on that list. One more strange signal in a growing catalogue of strange signals. No one looking at those numbers could have guessed that this particular source would later turn out to be one of the most extreme objects we've ever discovered. But that's how the universe often introduces its biggest characters, not with thunder and drama, but with a quiet notation, a label, a code. If you could float in front of Ton 618 today, protected from its radiation by whatever impossible shield your imagination likes, you wouldn't see a neat, tidy star. You'd see a quasar, a brilliant beacon at the heart of a distant galaxy. From far away, it would look like a single, piercing point of light, steady, unwavering, brighter than billions of ordinary stars combined. As you drift closer, that point would slowly widen into a disk, a flat, glowing whirlpool of gas and plasma spiraling into the black hole. This is the accretion disk, the place where matter swirls at nearly the speed of light, rubbing against itself, heating up to incredible temperatures, and releasing torrents of energy. Far from the center, the disk would shine with a bluish-white glow. Closer in, the light would shift beyond what human eyes can see, into ultraviolet, then into X-rays, so energetic they could strip atoms apart. Above and below this disk, you might see jets, twin beams of particles and radiation, fired out along the black hole's rotation axis. Like lighthouses that don't quite know how to stop shining. They can stretch for millions of light years, thin and ghostly, carrying energy far into intergalactic space. And somewhere at the very center, hidden from view, is the black hole itself, Ton 618's heart. You would not see it. You would not see edges or surfaces or features. Only a region where light disappears and where space curves so sharply that every path leads inward. From our distance here on Earth, Ton 618 is impossibly far away. Its light has been traveling longer than life has existed on our planet. We receive only a handful of its photons per square meter per second. Yet with patient instruments and careful analysis, we can read that faint glow like a letter sent across the ages. Inside it are clues to the black hole's mass, its distance, its speed, and the chaos whirling around it. Somewhere in that glow, hidden beneath numbers and graphs, is the quiet realization that what began as a simple entry in a catalog is, in fact, a cosmic giant, a black hole with the mass of roughly 66 billion suns, a monster so huge that the entire orbit of Neptune could fit inside its event horizon with room to spare. And all of that begins with a name, Ton 618. Almost boring, almost nothing. The universe, it seems, has a habit of hiding its most astonishing secrets behind the calmest labels. Chapter 2. The Heart of Gravity. At the center of Ton 618 lies something our language is not really designed to describe. We call it a singularity, a place where the density of matter becomes so high and the curvature of space-time becomes so extreme that our equations simply give up. Numbers go to infinity. Concepts we normally trust, distance, location, inside, outside, start to lose meaning. If you imagine a black hole as a kind of cosmic funnel, then the singularity is the place where that funnel narrows to a point. Everything that falls in, no matter how different it once was, gas, stars, light, even information, is forced into a single destiny. But this picture is only a metaphor. In reality, the singularity is not a dot floating inside a cavity. It's the part of our description of the universe that breaks, a sign that we've reached the limit of what general relativity alone can say. Physicists sometimes talk about the singularity as the edge of our understanding, not necessarily the edge of nature. Something must exist there, some structure, some process, some behavior of space-time that our current theories can't yet describe. Right now, our best descriptions of gravity, Einstein's general relativity, and our best descriptions of the quantum world, quantum mechanics, live in separate worlds. They both work beautifully in their own domains, but when you push them together into the extreme conditions inside a black hole like TON 618, they collide. To truly understand the heart of TON 618, we'd need a theory of quantum gravity, a framework that can describe space-time itself in quantum terms. We don't have that yet, so instead, we carefully trace the edges. We calculate how matter moves as it approaches the event horizon. We model the way space-time curves, the way light bends. We calculate the radius of the event horizon, the so-called Schwarzschild radius, using a surprisingly simple formula that depends only on mass and a few constants of nature. For a black hole the mass of a few suns, that radius is only a few kilometers. For TON 618, the radius is billions of kilometers. And yet, the same equation applies. The same relationship holds. Double the mass, double the radius. The enormity of TON 618 doesn't complicate the math, it just scales it up. That's part of what makes it so quietly beautiful, an unimaginably large object described by the same clean formula that would describe a tiny, stellar mass black hole. From the outside, what we see is energy in motion, the blazing accretion disk, the jets, the way it warps the light of background galaxies into stretched arcs and rings. From the inside, if such a perspective could exist, the picture would be very different. There would be no stable orbits, no escape routes, no outside to travel back to. Everything would be drawn deeper into the curvature of space-time, following paths that all end in the same place. The deeper you go, the more the idea of place dissolves. Inside TON 618, gravity isn't just a force, it's the shape of reality itself. And at its heart, somewhere beyond the limits of our equations, lies whatever the universe becomes when it is compressed beyond anything we can now imagine. We don't know what that is. We only know that it exists, and that its silent presence governs everything we can see around it. Chapter 3: Echoes in the Dark. When astronomers say, "We have detected TON 618, what they really mean is something much quieter. We have found its echo. Light doesn't come with a label. There's no little tag on a photon that says sent by TON 618, 10 billion years ago. The universe is full of light, all of it overlapping, scattering, and blending. So how do we find one black hole's whisper in all that cosmic noise? We start with radio waves. Back in the mid-28th century, radio astronomers began mapping the sky at long wavelengths. They found points of intense emission that didn't match known stars or galaxies. TON 618 was one of these, a bright radio dot against a seemingly empty background. Then came optical observations with more powerful telescopes. That dot was measured, its spectrum spread out into a rainbow of colors and dark lines. Those lines were shifted, dragged toward the red end of the spectrum by the expansion of the universe. The amount of that shift told astronomers how far the light had traveled. For TON 618, the redshift is so large that its light has been stretched by more than a factor of 3 on its journey to us. That stretching corresponds to a look-back time of over 10 billion years. Once we know the distance, we can convert apparent brightness into true luminosity, how much energy the object is really putting out. For TON 618, the answer is staggering, around 100 trillion times the luminosity of the Sunday. Then we add X-ray observations from satellites orbiting above Earth's atmosphere, picking up high-energy photons from near the event horizon. We add ultraviolet measurements. We add more detailed radio maps. Each wavelength gives us a different slice of the story. Radio waves trace the jets and the extended lobes of plasma far from the black hole. Optical light shows us the bright core and the surrounding galaxy. X-rays reveal the innermost regions of the accretion disk, where temperatures soar. Together, they form a composite portrait, not a photograph in the usual sense, but a set of layered signals that can be turned into images, spectra, and models. To measure the size of the region emitting this light, astronomers use a technique called reverberation mapping. They watch how the brightness of the core changes over time and how surrounding gas responds with a delayed echo. The delay tells them how big the system must be. Longer delay, larger structure. For Ton 618, the delays are enormous. The gas responding to the core's flickers sits light years away, yet still bound to the black hole's gravity. The light that reaches us is incredibly faint by the time it arrives, a few photons per square meter per second. Our detectors must be cooled, shielded, and integrated over long exposures to tease out these signals from background noise. But if we are patient enough and careful enough, the universe rewards that patience. Those whispers in the dark become clear patterns. Patterns become numbers. Numbers become understanding. In this way, Ton 618, an object we will never touch, never visit, never see, directly becomes knowable. We learn its mass. We estimate the rate at which it feeds. We trace the shape of its environment, all from the faintest of echoes, gathered here on a small planet, under a thin atmosphere, around an ordinary star. It's easy to forget how delicate that connection is. One photon, then another, crossing 10 billion light years of expanding space, just to end their journey as a tiny electronic signal in a human-made detector, and finally as a line on a graph, a point in a paper, a thought in a mind. The universe speaks softly. We just had to learn how to listen. Chapter 4. Quiet Architects of Galaxies. When we look at a galaxy from the outside, it seems calm, a graceful spiral, arms curving outward in slow motion, or a smooth ellipse, like a cottony smudge of light. Stars circle peacefully, gas clouds drift, everything looks settled. It's easy, from a distance, to imagine that galaxies are shaped mostly by their stars, by the million or billion or trillion points of light that we can see. But deep in the center, hidden behind clusters of stars and veils of dust, lies something that often matters even more, a supermassive black hole. For a long time, astronomers weren't sure how common these central black holes were. They seemed exotic, perhaps rare. But as measurements improved, a clearer picture emerged. Almost every large galaxy appears to host a supermassive black hole at its core. Some are active, blazing as quasars, like Ton 618. Others, like the one in our own Milky Way, are quieter, dim, almost dormant. But they are there, anchoring their galaxies with invisible weight. Black holes are often described as destroyers, devouring stars, swallowing light, tearing matter apart. And locally, that's true. Close to the event horizon, they are the ultimate consumers. But on the scale of a galaxy, black holes are also organizers. Their gravity helps hold the central regions together. Their energy output regulates how gas cools, collapses, and turns into new stars. Their jets and winds stir the interstellar and even intergalactic medium, preventing the galaxy from using up its gas too quickly. Astronomers have found a remarkable relationship between the mass of a galaxy's central bulge, its dense inner region, and the mass of its black hole. This is known as the M-sigma relation. The bigger the bulge, the bigger the black hole, and vice versa. This correlation suggests that galaxies and their black holes don't grow independently. They co-evolve, influencing each other through gravity and feedback. The black hole feeds on gas funneled to the center. In turn, the energy it releases heats and pushes gas away, slowing further star formation. In this delicate push and pull, galaxies find a kind of balance. Ton 618 is this process taken to extremes. Its mass is so large that it doesn't just sit at the center of its galaxy, it defines it. Its gravity reaches far into the surrounding space, shaping the orbits of stars and gas clouds. The radiation from its feeding phase heats not just nearby gas, but regions far beyond, affecting how new stars can form. In this way, a black hole that destroys matter in its immediate vicinity can create order on a larger scale. It can prevent galaxies from growing too fast, burning too bright, and exhausting themselves. It acts as both engine and regulator. Our own galaxy bears signs of this same process. At the center of the Milky Way lies Sagittarius A*, a black hole with about 4 million solar masses. It's quiet now, but the scars of past activity remain. Hot gas, strange radio structures, evidence of ancient outbursts. Looking at Ton 618 is like looking at that same story, but at a much earlier, more dramatic chapter. An era when galaxies were young, black holes were more actively feeding, and the universe was still in the process of building its grand architecture. Black holes, for all their violence, are the quiet architects of the cosmos. They leave no blueprints, they sign their work in gravity and light. But without them, the galaxies we see, including the one that cradles our sun, would not have the shapes, the histories, or the stability they do. They are the unseen hands behind the spirals of stars, the hidden cores around which cosmic cities assemble and endure. And Ton 618, colossal and distant, is one of the greatest architects of all. Chapter 5. Measuring the unmeasurable. How do you weigh something you can't see, can't touch, and can't approach? How do you measure the mass of a black hole that sits 10 billion light years away in a galaxy we will never visit, shining with light that left it before our planet even formed? The answer is a kind of gentle, persistent detective work, a chain of reasoning, step by step, each link based on physics we can test closer to home. We begin with brightness. Telescopes measure how much light Ton 618 sends us, not in some poetic sense, but in precise units: flux, energy, per unit area, per unit time. Once we know its apparent brightness and its distance, we can calculate its luminosity, the total amount of energy it emits. For Ton 618, that luminosity is about 100 trillion times that of the Sunday. Then we ask, if this light comes from matter falling into a black hole, how much mass must be converted into energy each second to sustain this output? We know from Einstein's famous equation, E equals mc2, E equals mc2, E equals mc2, that mass and energy are equivalent. We also know that accretion disks around black holes convert a certain fraction of the infalling mass into radiation. Not all of it most still falls in, but a predictable portion, depending on the black hole's spin and the geometry of the disk. Using this efficiency, we estimate the accretion rate, how many suns worth of material per year must be falling in. Then we invoke something called the Eddington limit. This is the point where the outward push of radiation on infalling gas balances the inward pull of gravity. If the black hole shines too brightly, radiation pressure can blow incoming matter away, limiting how fast it can feed. For a given luminosity, there is a corresponding mass that can hold on to that accreting gas without losing it. Putting these pieces together, luminosity, efficiency, Eddington limit astronomers infer the mass of the black hole. For ton 618, the numbers point again and again to a mass in the tens of billions of suns. To refine that estimate, we look at spectral lines in its light. Gas clouds around the black hole absorb and emit light at specific wavelengths, leaving fingerprints in the spectrum. Those lines are not sharp, but broadened, smeared out because the gas is moving at high speeds. The width of these lines reveals how fast the gas is orbiting. The faster it moves, the stronger the gravity holding it in place. From that speed and the size of the region inferred from reverberation mapping, we can use Newton's laws and general relativity to estimate the central mass. Here, too, ton 618 refuses to be small. The gas is moving at a significant fraction of the speed of light. The region is enormous. Only a black hole with tens of billions of solar masses could produce such an environment. Every step of this process carries uncertainty. Is the accretion disk exactly the shape we assume? Is the gas distributed in the way our models suggest? Are there hidden factors altering the observed light? Astronomers account for these uncertainties by giving ranges, not exact numbers. Perhaps ton 618's mass is a bit lower than 66 billion suns. Perhaps it's higher. But even at the lowest estimates, it remains one of the largest black holes ever measured. In some ways, the precise number matters less than the fact that we can say anything at all. From a planet orbiting an average star, in a galaxy that is ordinary by cosmic standards, tiny creatures made of recycled star stuff have learned how to measure the mass of an invisible object so far away that its light began traveling when the universe was young. We do it by trusting that the laws of physics are the same everywhere, that hydrogen behaves the same near ton 618 as it does in our labs, that gravity curves space-time in the same way there as it does here. So far, the universe has rewarded that trust. Our models, tested again and again, continue to work. Ton 618 stretches them to their limits, but does not break them. And if, someday, a new telescope or a new technique revises its mass, nudging it upward or downward, that too will be part of the same quiet process, refining our understanding, one photon at a time. Chapter 6. Time Travel by Starlight. When you look up at the night sky, you are never seeing now. You're always seeing then. The light from the moon takes about 1 second to reach you. From the sun, a bit over 8 minutes. From distant stars, years or centuries. From other galaxies, millions of years. Every point of light is an old story, still arriving. With ton 618, that story is ancient. The photons that reach our telescopes tonight began their journey more than 10 billion years ago. When they set out, the universe was only a fraction of its current age. Our sun did not exist. Earth did not exist. The Milky Way was still growing, merging, and changing shape. Back then, the cosmos was busier, denser, and arguably louder. Galaxies were closer together. Collisions were more common. Star formation rates were dramatically higher. The cosmic web, that giant network of filaments and voids made mostly of dark matter and gas, was still sharpening its structure. Gas flowed along those filaments, gathering in deep gravitational wells where galaxies formed and grew. Ton 618's host galaxy likely sat at one of those intersections, a node in the web where matter streamed inward from many directions, providing a rich supply of gas for both star formation and black hole growth. When we measure the redshift of TON 618's light, seeing how much its wavelengths have been stretched by the expansion of space, we are not just finding its distance, we are placing it on the universe's timeline. Its redshift tells us how long the light has been traveling, and therefore how long ago we are seeing it. To observe TON 618 is to look back into a more turbulent era, when quasar beacons were more common, when the universe glowed more brightly in ultraviolet and X-rays, and when gravity and gas were still negotiating the large-scale structure we inhabit today. We sometimes call this kind of observing cosmic archaeology. Just as digging deeper layers into the ground reveals older artifacts, looking to greater distances reveals earlier epochs of the universe. TON 618 is one of the deeper layers, a relic of an age when black holes were feeding rapidly, shaping both their galaxies and the intergalactic medium around them. It's important to remember that the TON 618 we study is not the TON 618 that exists now, in this present moment. The black hole itself almost certainly still exists. Black holes do not vanish quickly, but its environment may have changed. The accretion disk might have dimmed as its fuel ran low. The jets might have weakened or switched off. The host galaxy may have merged with others, altering its shape. We can't see any of that yet. All we see is the TON 618 of 10 billion years ago, frozen in light that has only just arrived. In that sense, astronomy is always a kind of time travel, but one where we can only go backward and never arrive in person. We stay here. The light comes to us. Our telescopes are like windows into stacked layers of time, each one representing a different distance, a different age. Closer galaxies show us a more mature universe. Distant quasars like TON 618 show us a younger one, still blazing with raw energy. Somewhere between those extremes, we sit in a brief, quiet interval where the universe is transparent, structured, and cool enough to allow planets, oceans, forests, cities, and late-night thoughts about black holes. We exist in the era when the lights are still on and the ancient signals are still arriving. If you step outside on a clear night and look into the darkness, you won't see TON 618 with your eyes. It's much too faint, too far, too red-shifted, but you can know that, in that direction, its ancient light is still crossing the void, and knowing that changes the darkness. It turns empty space into a corridor of time filled with stories, still in transit, memories preserved in photons, traveling endlessly through a universe that is both older and stranger than it appears. Chapter 7: A Hungry Young Universe. If you could go back to the era when TON 618's light began its journey about 10 billion years ago, you would find yourself in a universe that feels nothing like the one we know today. The cosmos was younger, denser, and hungrier. Everything was closer together. Galaxies were forming fast. Matter was collapsing into stars at astonishing rates. Gravity ruled every direction like an impatient sculptor. Picture immense rivers of gas flowing along the cosmic web, those filament-like highways of dark matter and hydrogen stretching across the early universe. At the intersections of these filaments, matter pooled into deep gravitational wells. These pools became galaxies, and inside those galaxies, deeper wells formed around the earliest black holes. TON 618 was born in such a place, where the cosmic web funneled vast amounts of primordial gas into the heart of a young galaxy. This river of fuel flowed inward relentlessly, igniting waves of star formation and feeding the central black hole faster than anything we see in the modern universe. The universe back then wasn't quiet. It wasn't cold. It wasn't peaceful. It was vibrant, crowded, and bursting with creation. Stars ignited in massive clusters, bright, blue, short-lived giants burning through their fuel in a few million years. When they died, their explosions enriched the surrounding gas with heavier elements, making the next generation of stars more complex. Black holes formed from the collapse of those giants, merging, colliding, and growing. The black hole that would become TON 618 likely started with a head start, either as a direct collapse black hole formed from a huge primordial gas cloud collapsing straight into a black hole without forming stars first, or a supermassive seed formed from multiple early black holes merging together. Whatever its origin, TON 618 grew far faster than models once thought possible. Its accretion disk blazed like a cosmic furnace, releasing so much energy that it shone brighter than entire galaxies. That energy did not remain local. Quasar winds and jets spread it across millions of light years, heating the intergalactic medium, stirring turbulence in nearby regions, and influencing how neighboring galaxies formed. In the early universe, this kind of feedback shaped everything. TON 618 wasn't just a consumer, it was a participant in the cosmic ecosystem. Its hunger carved structure into the young universe. And while the modern cosmos feels calmer, slower, more settled, the energy from that era is still reflected in the large-scale structure we see today. The galaxies that survived, the elements we breathe, and the stability we enjoy all come from those early, fiery chapters. The young universe was hungry because it was growing, and TON 618 was one of its biggest appetites. Chapter 8. The Edge of What We Know. For all our telescopes, equations, and simulations, TON 618 sits close to the boundary of human understanding. Not just physically distant, but conceptually distant. It challenges our models in quiet but persistent ways. It grows too fast. It shines too brightly. It appears too early in cosmic history. According to the simplest theories, a black hole shouldn't be able to reach tens of billions of solar masses within just 3 billion years after the Big Bang. There isn't enough time. There isn't enough fuel. There isn't enough stability for constant feeding. Yet, and this is one of the universe's favorite answers, it happened anyway. TON 618 forces us to reconsider how black holes form, how fast they can grow, how early galaxies gather massum, whether the known limits, like the Eddington limit, can be exceeded under extreme conditions. Some theories propose super Eddington accretion fuel flowing inward so quickly that radiation pressure can't stop it. Others suggest massive seeds from direct collapse, forming black holes millions of solar masses at birth. Still others explore exotic possibilities. Dense dark matter halos, early cosmic inflows, or brief periods where radiation became trapped in collapsing gas. Every explanation is plausible. None are proven. Each one sits at the boundary between what we know and what we hope to know. Black holes like TON 618 also push us toward another frontier, the unification of physics. Einstein's general relativity describes gravity beautifully, how mass bends space-time, how time slows near heavy objects, how matter orbits, curves, but it breaks down at the singularity. Quantum mechanics describes the small-scale world, the jitter of particles, the uncertainty in measurements, but cannot handle infinite density or the collapse of space-time into a point. Inside a black hole, these two great frameworks collide. TON 618, enormous and unreachable, is the perfect laboratory for the universe's most challenging questions. What happens at the singularity? Is space continuous or made of discrete units? Does information really vanish behind the horizon, or is it somehow preserved? Is the universe one smooth continuum, or woven from quantum threads? Are black holes portals, boundaries, or just endpoints? Every extreme object like TON 618 nudges these questions forward. Astronomers sometimes describe the edge of what we know not as a line, but as a landscape, always shifting, always expanding, revealing new mysteries even as old ones are solved. TON 618 sits like a mountain at the border of that landscape, massive, mysterious, silent, a challenge not in violence, but in scale, a reminder that the universe is under no obligation to fit neatly into our theories. And each time we point a telescope toward that distant beacon, we are quietly rewriting the map of what is possible. Chapter 9. Falling into TON 618. This is where imagination meets physics. If you could approach TON 618 not with a real spacecraft, which would be destroyed long before arrival, but with a thought experiment vessel immune to radiation and gravity, you would see one of the strangest landscapes the universe has to offer. From afar, the black hole would look like a star, a single, steady point, except its brightness wouldn't flicker. It would be impossibly constant. As you drift closer, that point would widen into a disk flat, bright, and spinning at nearly the speed of light. The colors would shift as you approached, bluish-white far out so, ultraviolet nearer into, X-rays screaming from the edge of the event horizon. This disk is hotter than any star, full of stripped atoms and magnetic storms so strong they twist space itself. You would hover above it, protected by that imaginary shield, and watch space curve around you. The far side of the disk would appear above the black hole, a gravitational mirage caused by light bending around the horizon. Up, down, left, right, these directions would start to lose meaning. Then, if you let yourself fall inward, at first, you would feel nothing. Gravity pulls on every part of you equally, so you would be weightless. You would accelerate, but with no sense of motion. The universe behind you would shift redward, fading in color. The event horizon would approach, but not dramatically. There is no visible surface, no shimmer, no barrier. Nothing tells you where the edge is. Then, without any sensation, you cross it. From the inside, everything continues normally. From the outside, your fall appears frozen forever. Two equally valid realities coexisting. Inside, time and space trade roles. Every possible future leads inward. No path ever leads outward again. TON 618 is so large that tidal forces near its horizon would be surprisingly gentle. You would not be torn apart instantly. You could fall comfortably, seeing distorted light from the disk above you. But the deeper you go, the stranger everything becomes. Light blue shifts, brightens, compresses, space narrows, time stretches. Your future becomes a single direction. Eventually, the laws of physics as we know them collapse into infinities. Relativity predicts unending curvature. Quantum theory refuses to accept that answer. At this point, equations fail. Reality becomes something we cannot yet describe. Perhaps matter becomes a quantum core. Perhaps space-time connects to somewhere else. Perhaps information is preserved at the horizon. Perhaps the singularity is not a place, but a process. The truth is hidden, not because the universe is secretive, but because the laws that govern the inside of a black hole are simply not yet complete. To fall into ton 618 is to follow physics to its limits, and then step beyond them, into the place where our knowledge ends and wonder begins. Chapter 10. The Stillness Beyond Light. Outside a black hole, everything we see, the glow, the jets, the radiation, is a reaction to something we can't see. Inside the horizon, there is no light, not because it disappears, but because it can no longer move outward toward us. The event horizon isn't a wall, it isn't a surface, it isn't even a thing. It's a boundary in space-time where every possible path leads inward, a place where visibility ends, but physics does not. From an outside perspective, everything near the horizon appears frozen, slowing, fading, red-shifting into darkness. From the inside, everything continues, falling, converging, moving toward equilibrium. This stillness, this absolute inwardness is not emptiness. It is accumulation. Every particle that has fallen into ton 618 still contributes to its gravity. Every bit of matter continues to exist, though transformed beyond recognition. Black holes are often described as voids, but in truth, they are the densest concentrations of matter the universe allows. Inside, motion and time behave differently, but they obey the same equations, right up to the singularity. Only at the very core do those equations truly fail. Even then, the stillness is not chaos. It is order pushed to its extreme. Outside the horizon, the influence remains enormous. Ton 618 shapes the orbit of every star in its galaxy. It bends light across unimaginable distances. It sculpts the flow of gas for millions of light years. Its jets can regulate star formation in nearby regions. The stillness inside gives meaning to the motion outside. Without that boundary, the blazing disk and relativistic jets wouldn't exist. In this sense, the black hole is both invisible and essential. A silent anchor holding galaxies together, a regulator of cosmic energy, a final reservoir of mass when all else fades. Even in a far future where stars burn out, galaxies drift apart, and the universe cools into darkness, ton 618 may remain slowly evaporating through Hawking radiation over unimaginable timescales. Long after light is gone, the stillness may still endure. Chapter 11. We Who Listen. There is something profoundly human about looking at a faint signal in the night sky, a signal that left its source before our species existed, and turning it into understanding. Every photon from ton 618 began near the edge of a black hole and traveled through collapsing gas clouds, through forming clusters of galaxies, through expanding space, through filaments of dark matter, through empty voids, through billions of years of change, before ending its journey in a human-made sensor. It touched mirrors polished to within nanometers of perfection. It was converted into an electronic pulse. That pulse became data. Data became graphs. Graphs became knowledge. Knowledge became understanding. And understanding became wonder. This process, quiet, patient, delicate, is one of the universe's most astonishing phenomena. The cosmos is literally communicating with itself through us. The atoms in your body were forged in ancient stars. The neurons in your brain fire according to the same physics that bends light near black holes. The curiosity you feel is made of the same particles that once fell into quasar disks. We are not separate from the universe. We are one of its ways of knowing itself. Every time we measure ton 618, we are not just studying a distant object. We are participating in a conversation that began before Earth existed, and will continue long after humanity's final chapter. This is why even the faintest signal matters, why even the most distant light feels strangely personal. It connects us not by metaphor, but by physics to the past, the present, and the future of everything. Chapter 12. A story that never ends. The light from Ton 618 is still traveling, still crossing the dark, still carrying the memory of a universe that was young when it began its journey. Long after we are gone, long after our cities fade, long after our star grows old, that light will still be moving outward. Perhaps it will reach another world, another civilization, another set of curious beings asking the same questions we ask now. Perhaps they will measure its redshift, decode its spectrum, trace its path across time. Perhaps they will marvel at this quiet beacon from the early universe, just as we do. Or perhaps no one will be there to catch it. Perhaps the universe will carry it forever, unobserved but still real. The story doesn't depend on us, but our awareness of it gives it meaning. As you rest here now, breathing softly, you are part of that same long story, a story written in starlight, shaped by gravity, carried forward by curiosity. Ton 618 is one chapter, you are another. The universe continues through both. There is no final line, no ending, only continuation. The light traveling, the questions forming, the stillness beyond light holding everything together. So let your thoughts drift like photons crossing the dark. Let the quiet of the cosmos settle around you, and know that somewhere out there, Ton 618 still shines, unseen, ancient, patient, waiting across the endless night. A reminder that the universe is vast, that we are small, and that curiosity is the bridge between the two.